mind seem to grow giddy by staring so far into the abyss of time? John Playfair, 1788. I can think of no better place than the rim of the Grand Canyon to stare into that abyss and to try to explain why we might want to think of time as the axis on a graph. The Grand Canyon, we have thousands and thousands of sedimentary rock layers stacked up one on top of the other. And it's pretty obvious the oldest layers are at the bottom, and they get progressively younger as we go up the walls of the canyon. The trick is, how much time is actually represented here? Let's take a closer look at the rocks at the bottom of the Grand Canyon to explain the way geologists unravel Earth history. Here we have ancient metamorphic and igneous rocks in the inner gorge, overlain by the Tapeats Sandstone Formation. They're separated by an ancient erosional surface that we call the Great Unconformity. Now let's see if we can use clay to recreate the formation of the Great Unconformity. The layers are then crumpled during the formation of an ancient mountain range. Obviously, this took a long time, but how long? One way to measure time uses unstable atoms. For an example, we're going to use uranium. Uranium atoms are kind of like some of the people you might know. They're prone to just falling apart without warning. They just break down. In the case of uranium, through a series of steps, it'll break down into atoms of lead. If we have a mineral, for example, this is zircon, that contains uranium when it forms, then over time we can watch as the uranium atoms break down into lead. In our simulation, the white are the uranium, and you'll notice over time they break down into black, which are the lead atoms, and we can actually measure these, and the more black we have relative to the white, the longer it's been since our mineral formed. In this way, scientists can actually put numbers on geologic time. So this chart, which is called a stratigraphic column, shows all the different formations which are present in the Grand Canyon. But notice, the vertical axis is not time, it's rock thickness. Let's try constructing a graph of the rocks in the Grand Canyon using time as the axis of the graph instead of rock thickness. We can't imagine even 1 million years, much less a billion, so we need to convert time to distance so that we can visualize it. The oldest rocks in the canyon are about 2 billion years old, and we have 200 centimeters of paper. 2 billion years divided by 200 centimeters should give us 10 million years per centimeter. Okay, so what we're going to do now is construct a graph using time rather than thickness for the rocks in the Grand Canyon. And you'll remember we decided that the most convenient scale here was 1 centimeter equals 10 million years. So 30 centimeters would be 300 million years. So from here to here, from the 30 to the 40 would be 100 million years. Now we'll look up the latest accepted ages for the rocks in the Grand Canyon and cut out layers of construction paper to represent the amount of time each group of rocks represents. Plotted with time as the axis, it becomes obvious that only a small portion of Earth's history is recorded in the rocks of the Grand Canyon, even though the canyon is a mile deep. So we can think of time as a dimension, just like length, width, and height, that can be plotted on a graph with a scale of nanoseconds to billions of years. Time is an essential dimension for measuring change. not just for geologists, as you can see on these graphs, but for all scientists and engineers. And although Albert Einstein claimed that time is an illusion, I really think it's more practical to think of time as an axis on a graph. The mind seemed to grow giddy. God, what's wrong with me? All right, let's try it again. Okay, ready? Okay. The mind seemed to grow giddy. I don't know. I think I'm Alzheimer's.